Hey gamers, I'm back at you with another episode of the Real Hacker Hours podcast. Today we're going to continue porting Nightmare over from Python 2 to Python 3. For this, I'm going to be looking at the bof overflow call shellcode module. Effectively going to be going through these writeups, making sure that they make logical sense since I made a lot of typos while making Nightmare. And then I'm going to be porting any Python 2 sections over to Python 3. Let's start with Tamu 2019.3. So let's go into here and open up the README. Okay, and let's navigate to that submodule. Okay, here we are. Let's check out the binary. 32-bit. Only has pi and rel. And let's run it. Okay, cool. Doesn't have the check sec, so let's add that. Okay, there we go. So we're dealing with a 32-bit manner. Run it. It prints up what looks like a stack address and prompts us for input. Yeah, that looks like it. When we take a look at the main function ghidra, we see this. Okay, let's go ahead and throw the binary in ghidra. Close. Okay. Let me just take a second to load this into ghidra. Wait, no. Completely wrong area. What am I doing? Here. Okay, let's throw that there. Import the binary into the project, and now let's actually run it in ghidra. Analyze it. Okay, let's take a look at the main function. Here it is. Okay, looks like it primarily... Something isn't right. Oh, looking through the main function, the most important thing here is that calls the echo function. Let's take a look at that function in the function ghidra. I'm just going to go ahead and edit this. So looking through the main function, we see this. So it makes more logical sense. The most important thing here is that it calls the echo function. Let's take a look at that function in ghidra. Okay. And the echo function, this is where it actually happens. Okay. This decompilation looks similar to that, just this is going to be named input. By the way, the hotkey to rename variables in ghidra is L, or at least default. I'm pretty sure you can change the mapping. So we see this printf statement %p with the stack buffer, so this is a stack info leak, and then it calls gets. So what this is going to happen is we're going to effectively overthrow the return address, and since non-executable stack is disabled, we can execute code on the stack. So we are just going to load shellcode onto the stack and then overwrite the return address to point to that shellcode. Because of this stack info leak, we know the address space of the stack, so we know the address of where the shellcode is going to be stored, so we can do that. I'm just going to go ahead and read through here to make sure that makes sense. This is a bug since gets does restrict how much data it scans. and we get this. The question is what to call the functions. Shellcode is such a big so we need to have shellcode, and if we direct content, it will need to match the architectures. We need to have ARM for. I don't know why that ARM is there. Whenever I need to just grab it from, yeah. I can just Google for shellcode and make itself, which we will cover later. I'll be using shellcode by, yep, using shellcode from that guy. Now we can inject into memory. However, we just need to deal with ASLR. I just picked this as binary mitigation. What it does is it randomizes all the address for various memory regions. So while the address is random, the also see things in memory are the same. So I just look at go just from the memory space to know what it is. The thing, okay. Talks about how we're breaking ASLR, talks about how we're going to be using shellcode. This also applies to where our shellcode is stored in memory, which we need to know. Like for us, the address printed is the start of an input, so we can just take that address and overwrite it. That is true, it is printing the start of our input, so again, just use that address. Which space we have should be OX12E, which is 302 bytes, but let's see. Yep, OX12E. There are two saved. Yeah. With all this, we need to write an exploit. Okay, and yeah, this exploit, effectively looking at it, start off with our shellcode, and then we add additional filler to fill in the space between the end of the shellcode and the return address, and then we just drop the address of the leaked address that we got, which we parsed up with this, and then we just send it and solve the challenge. I'm going to go ahead and port the exploit over to Python 3. So what needs to change? I think this needs to change to a binary. And need the payload. Just convert this over to a byte string. For these simpler exploits, porting it isn't really that big of a deal. I need to throw my license on this Sublime Text. I do have a license, but since this is a new instance, a new poning VM, I haven't licensed it yet. I will do that after this recording. Actually, I'm going to go ahead and just pause it and register it real quick. Okay, I'm back. Yeah, threw my license in here. It got registered. Okay, cool. Now back to working on this. Okay, looking through this. Oh, we need to change this. This print statement adds parentheses. Yeah, it looks good. Let's go ahead and run the exploit. And oh, we need to switch this over from string to byte string. And we can see there that this exploit works, so I'm just going to go ahead and copy this over. And I'm going to copy over the Python 3 exploit. Cool. So that is Tamu 19.3 has been ported over. Next up, let's do Seesaw 2017 pilot. So Seesaw 2017 pilot. Okay, here we are. I'm going to open up the writeup and just take a second to open up everything. Sure. I'll save it. Okay, let's analyze it. Okay, while that's analyzing it, I'm just going to go ahead and run the binary real quick. File pilot, 64-bit. No mitigations, nice, nice. You run it. I think I remember this one. Location prints what looks like a stack address, takes input. I'm guessing if you give it enough, we will cause it to crash. Yep. Okay, let's take a look at the main function. Oh, it looks like it's not named. This is probably the main function right here. Okay, yeah, so what I effectively did, the main function name was stretched from the binary, so I just took a look at entry, which this is the first function that's actually ran, and it will call libc start main, which the first argument to it is the actual main function. This is just part of like the in the background functionality that actually like runs the binary. So this is main. I'm just going to go ahead and rename it. And let's just take a look here. What do we see? Looks like C++ code or something like that. Prints out a bunch of stuff. Good luck, pilot. Allows us to scan OX 40 bytes into local 28, which local OX. Oh, OX 40 bytes into local 28, which is OX 28 bytes away from the saved return address, which you can see there. So we can overwrite the return address with another function. And let's see, where was that info leak given? It was given after location. Where was location printed? I want to see what the thing that it is, yeah, what the value being printed there actually is. Good luck, pilot. Location. I think this is it, but I'm just going to do it. Look at the write-up, which does it dynamically. I think that would be a little bit easier in this scenario. So let's go ahead and look at the write-up since it's been a while. Let's take a look at the binary file. I want to include the check sec here. So you can see here they're dealing with 64-bit binary. When you run it, you see that it prints out a lot of text, including what looks like a function. Look. Oh, but last one. So here, when the write-up, I just explained it that we looked through the functions and just found this function, which has all of the strings that which it looks like it. We can also see. I'm just going to add a little part that explains how I found what the main function was this time, which we looked at entry. Looking at the entry function. Let me just wrap this properly. Okay, so that's entry function. We see the function which is part of the alpha for starting a binary. The first argument is the function six. Although I've renamed it to main for simplicity. Okay. Set the, okay. Here we can see the main function. Okay, cool. So right now in here I renamed OX00400986 to main. I'm just going to take a second and update that throughout this write-up since we see it called in multiple, referenced in multiple occasions. That way we don't have someone looking at this and being like, wait, these naming conventions aren't uniform or something. What did I name it here? Read input. I'm just gonna name this input. Hit the wrong key. Save changes, no. Input. Okay, we have that there. Okay, so we have that tidied up. Looking through here, we're going to see that it prints out. However, there are two important sections. The first is where it scans in data. Yep. Actually, let's copy this since when in this instance of ghidra analyzing the function, it automatically named the result output to something else. And this part, location. Copy this portion. Okay, looking at the stack layout, ghidra really doesn't look like there's anything between our input and this overflow. Oh, x28. Let's see if, yep. Which is what ghidra showed us. So we have a way to overwrite return address because we know where our memory is. Actually, what did it say here? OX DE80 stored at DE80. Let's take a look at that location. So, oh, it's printing out the actual input itself. So, like the previous challenge, it's just giving us the address of where our input is first being stored. Okay, cool. Let me just read through here. You can see, also you can see the address printed for the start of our input and memory on the stack. Okay, cool. One thing that we would typically have to do when we're trying to break ASLR is when we get an info leak, we'd have to figure out the offsets between like whatever we leaked and the address we want to know. However, in this case, in the case of the previous challenge, the address it's leaking is the address we want to know, so we don't have to deal with any offsets. We do replace star, even know where it is. With this, we can write an exploit. Okay, cool. So here it just only thing left to do is port the exploit over to Python 3. So let's go ahead and do that. First thing is first. Print needs to have parentheses. This looks good. This needs to be changed to byte array. This needs to be changed to byte array. Okay, shellcode is from here. Yeah, I did not write this shellcode. I got it from where the write-up says I got it from. And that looks like we have ported it. Let's try it. Clear Python 3 exploit. Okay, we see that we have popped a shell. So I'm going to copy this and paste it here. Okay, so that one is ported, so that's 2 of the 3. Last one is TU18 Easy Shell, so let's look at that. Gonna take a second to get it loaded. Oh, shell it easy. Yeah, I remember the previous challenge because I remember when I was trying to solve it back when I was developing an autoponer and get my autoponer to solve it. The static analysis I had for detecting info leaks wasn't working, so I actually had to write a dynamic analyzer to dynamically detect info leaks. And I remember that challenge, trying to solve that challenge with my autoponer, is primarily why I had to write that functionality. Yeah, it was fun. Okay, shell it easy. Let's run it. Shell easy has not been analyzed. Would you like to analyze it now? Okay, so that's being analyzed. I'm going to go ahead and open up the write-up here. Modules 06. Shell easy. Let's open that up and the exploit. Okay, cool. So let's take a look at the binary first. Okay, gives us an info leak, and I'm pretty sure if we give it a ton of input, it'll crash. Okay, looks like we need to give it more. Okay, let's see. No binary mitigations, 32-bit, and okay, cool. So let's take a look at it in ghidra. Functions, is there a main function? Yes, or there's always a main function, it's just a question of if it's labeled that. Okay, so we see here gets, calls gets. Okay, prints out the start of our input, calls gets. Pretty sure this is the same shellcode deal, basically the same solution that we had for the previous 2 challenges. And input is, so we're gonna have OX4C bytes of input, actually shellcode, then filler up to OX4C bytes of input, and then the start of our input is going to be the return address, and that's going to be the exploit. Let's take a look through our write-up to make sure that it makes logical sense and we didn't overlook anything. So we can see that we're dealing with 30-bit run. It prints out what looks like a stack address and prompts us for input. We can take a look at the main function. We see this. That looks right. So this is pretty similar to the other challenge of the module. There is a char array input which can hold 64 bytes, which it prints. I'm just going to read quietly. Okay, so there's a slight part. Okay. Oh, okay. So here, okay, I made a mistake. There is something I overlooked. So looking at this main function right here, the one I have there, exit is called directly after get, so return address is, oh, the ret is never executed, so return address is never executed. However, this is a decompilation mistake. Looking at the assembly code here, there is a comparison done, and if the compare, if we pass the check, it will actually return. Jump it, yeah, I compare jump of 0, jump to here, then it rets, if not calls exit. Here, in this decompilation, This is an updated version of ghidra, so there's probably some fixed on, so will not make the same mistake. So this is a slight complication. Where is local C? Local C is at OXC. Okay, that should be plenty far enough. So we should probably have shellcode, which will probably be like 20 bytes or something like that. Filler to OX negative OXC onto the stack. We have this value which looks like dead beef or something like that. What is the octo? Never mind. It's equal to, yeah, dead beef. And then we're going to have filler to the return address after that, and then the actual return address which will be the start of our input. So we can see there's a check to see. When we look at the stack layer in ghidra, we see that this variable is within our means overwrite and is an offset of OX40. Yeah, it's an offset of OX40 from the start input because OX4C minus OX0C equals OX40. So we just need to overwrite it with OX deadbeef and we should be good to go. Now let's find the offset between the start of input. It's going to be OX4C. Excuse me. Yep, OX4C. Which matches the ghidra offset. That we have everything you need to make the exploit. So last thing to do here. Put down. Okay, and here I just added a little extra piece at the end just to like, hey, this is actually like our shellcode that we can see after it's been loaded in. Here I do examine as instruction, which is a will effectively look at a piece of memory and look and interpret it as instructions. Because you can see here, this is x86 shellcode, and yeah, let's go ahead and import the exploit. Import all. Convert this over to byte array. Okay, that looks about right. Let's try running it. Okay, we see that this runs just fine. Okay, I'm going to go ahead and update it, and we'll be done porting this module. And let's copy this over. Okay, cool. So this is done. This is the last submodule of the buffer overflow into shellcode module. So we ported that entire module over. I'm going to go ahead and cut off the episode here. Thank you, gamers, for watching.